Hello everyone. In the previous video, we had discussed the problem of a plate with a circular hole in it under uniaxial tensile loading, and we had mentioned how that problem is a precursor to an entire field of mechanics called fracture mechanics. In much the same way, in today's lecture also we are going to discuss a very special problem called the Flamant problem, which will again be a precursor to another field of mechanics called contact mechanics. So let me write that down here, contact mechanics. Now this is a tremendously important area of research, of professional engineering application, because you understand that especially within the context of mechanical engineering, you have such a multitude of applications where two bodies are coming into contact with each other, with the resultant stresses, the various deformations coming into the picture, and all of that falls under the broad purview of this contact mechanics. Going beyond mechanical engineering also, if we go into the field of soil mechanics, of geophysical sciences, of civil engineering, there also you will find that this Flamant problem is like the introductory problem to an entire field of study where people do various interesting and important, professionally important things related to structures as they stand on ground, various loadings taking place on the earth, etc., etc. So with this kind of a motivation, let me write that down also here. So this kind of a problem has applications in geophysical sciences, civil engineering, etc., etc. Okay, so what is this problem? What have I depicted here? So this horizontal line, this horizontal straight line that I have drawn, that basically you can think of it like the boundary of a half space. So what I mean by a half space is that the entire portion which is beneath it, it could be above it also, but in this particular case it is beneath it. So the entire portion which is beneath it, that is actually the solid material. Okay, I'm not drawing it by hatch because it will unnecessarily clutter the diagram. I have to draw other things also here. So you understand that this is the half space region. Okay, so you can imagine that so if there had been no boundary here, if this had been all one continuum, so that would have been the infinite full space, and because there is the solid material present only beneath it, that is why this is the infinite half space. Okay, now on this half space, okay, so we are looking at it from sideways. Okay, so on this half space we have this kind of a load, okay, and the question that we ask ourselves is that as a result of this load, what is the stress distribution in this entire half space region? Okay, and that's a very important question. So you can imagine that maybe some kind of pole is standing here having some weight, or some building is standing here on the ground having some weight. So what will be the stresses generated in the ground beneath it? Furthermore, closer home to mechanical engineering, suppose you have some kind of indenter acting on a flat surface which has some depth, and maybe the dimensions and the loading of that indenter is such that the thickness of the material is also such that it can, for all practical purposes, be considered to be some sort of a half space or infinite half space. Then also this is a good enough model for that situation. You also note that this is just like the two-dimensional projection of the actual situation. So you can think of it that so maybe I can just clarify the three-dimensional picture. So suppose I have this kind of a ground or some surface, and there is material beneath it. There is material beneath it going to infinity. Okay, like this. And it is on this surface that I have this distribution like a line loading. Okay, so this is like a line loading. And this goes off to infinity here, this goes off to infinity here, just like the surface also goes off to infinity here, goes off to infinity here. So when you look at it from this side, this entire picture will look like this. Okay, so this is the part, the bottom is the part where I have drawn those kinds of okay, so these vertical lines, they correspond here. Okay, it's like that. All right, I won't clutter the diagram any more than this. Now, how do we address the problem of finding the stresses in this region? So for that, what we'll do is we will from the very beginning exploit the symmetry of the situation. So suppose you consider that that our x-axis is oriented like this. Okay, suppose your x-axis is oriented like this. Then to the right of this and to the left of this, okay, the entire situation is perfectly symmetric, and we are going to exploit this. So how are we going to exploit this? So you understand that although I have written it like an x, and what I can do is I can imagine that if I consider a semicircular arc like this, okay, semicircular arc like this, centered at the very origin from which the x is originating, then all around this arc, okay, because of the entire symmetry of the situation, the stress distribution is going to be the same. Okay, well, it is not so simple like that. Okay, there will be some variation along this, but whatever it is, suppose you consider a point here, maybe at a certain angle theta from this x-axis. If you consider the same a corresponding point on this side at the same angle theta from this x-axis, the situation here and the situation here is going to be the same, but of course there is going to be variation all along this arc. Okay, so we are now in a position to actually utilize our machinery of solution of the 2D elasticity solution in polar coordinates in this kind of a setup. Okay, so the thing will be clear only when we do the actual solution. And talking about the solution for this particular very special problem, we have to proceed in a special way, which will be somewhat different from the usual way we have been proceeding till now. So what are we basically trying to do here? You see, if I have to actually satisfy the force balance here, so to speak, then the condition, the fundamental condition that I need to satisfy is something like this. So this is the starting point of our whole solution. Okay, as I just mentioned, we have to proceed in a slightly different fashion here. So what I'm going to do is I'm going to consider a little elemental arc of r d theta. So let's say that this is theta. So this theta goes from minus pi by 2 to pi by 2 here, okay, in order to cover this entire arc. And this little bit here, that is my r d theta, where of course you note that this portion here is the r. Okay, so if we consider a bigger arc, that r is going to change. Alright, so this is the generic situation. Now in this situation, the force balance condition that has to be maintained can be written in an integration or in an integrated fashion in this way. So you understand like this. Suppose we isolate this semicircular zone. Okay, suppose we isolate this semicircular zone, then the only force that we are currently seeing is this vertically downward force P. Okay, so how is this force P going to be balanced? It is going to be balanced because of the traction conditions here, and those traction conditions you can understand that suppose you consider this little arc itself, so we'll have some kind of a sigma RR here. Okay, so that sigma RR, that sigma RR, when it is multiplied by the r d theta, it is going to give me, and of course you understand that there is a hidden unit length into the plane of the screen, but I'm not going to write that. So sigma RR into r d theta, it gives me the force in the radial direction. Okay, it gives me the force in this radial direction, but that is not what I want. I want the component of that force in the vertical direction. And what is the component of that force in the vertical direction? I have to multiply this thing by cos theta. Now we don't have to worry about the horizontal component, because as I already mentioned, when you consider the corresponding point or the corresponding or a corresponding element like this on this side of the x-axis, that will have a force like this, and that horizontal component will be in this opposite direction to what it is present here. So this force here is like this, that force here would be like that, and the horizontal component, okay, so the horizontal component here would be balanced or negated by this. However, the vertical component would still have to be considered, because both of them are in the same direction. So as we go from minus pi by 2 to pi by 2, as theta goes from minus pi by 2 to pi by 2, it is the vertical component which is getting cumulatively added up. Okay, so all that we have to do is take this integration from minus pi by 2 to pi by 2, and so this is plus P is equal to 0. All right. So now what we can say from here is that this entire thing is just going to be equal to minus P. So we can write that down alternatively. Okay, so this is just going to be equal to minus P. Okay, so this is the beginning of our arguments. We are not going to directly talk about the Airy stress function right away. Rather, we are going to consider this sigma RR itself. Right now we don't know what this sigma RR is. Okay, so how can we find it out? So this is like a little bit of detective work that we have to do here. You see, this entire integration is with respect to theta. Okay, so whatever we do here, after the integration has been done and after the proper limits have been put, the result of this integration will be such that the answer of this integration will not involve any theta dependence. Okay, so on the right hand side we see that very nicely there is no theta dependence, so at least that part is consistent. But on the left hand side, apparently there is some kind of a r dependence, but that r dependence is not present on the right hand side. So what to do? We have to somehow do something such that this r dependence, this very inconvenient looking r dependence on the left hand side, that has to go away, such that it becomes whatever is there on the left hand side, that becomes equal to the right hand side. Okay, because this right hand side is a given constant, it simply does not depend on r, it does not depend on theta. The theta, the independence of theta has been taken care of by the integration itself. But the independence of r, how do we take care of that? That is the question. So this is not actually a very hard question. What we can do is, we can think of it like this, that suppose if sigma rr is of this particular form, suppose it is of the form that in the numerator there is some function of theta. We currently don't know what that is. If we knew it, half our job would be done. But right now we don't know about it. So let's keep it like this, some unknown function of theta, but a pure function of theta. And in the denominator there is a r. So what is the motivation? Motivation is that the moment we do this, we replace this form here, this r is going to get cancelled with this r. Okay. So when that happens, automatically the answer that we'll get will be independent of r and certainly independent of theta. Okay, so this is our first achievement as deductive work. Okay, now what to do? Because till now you see we have not talked about the eddy stress function, and unless we talk about the eddy stress function, how can we solve the 2D elasticity problem? So we do have to talk about the eddy stress function. So we are going to approach this in a clever fashion. What we'll do is, we'll take a relook at the form, the general form of this sigma rr, as it depends on a general eddy stress function phi. Okay, so we go to our Jupyter notebook. I've already fired up a new file here. Let me import this polar utilities first. All right. Now let me first define a very general eddy stress function like this. Okay. Please note that this is not by default defined in the polar utilities package, so I have to actually do it. The r and theta, the r theta symbols are very much defined in the polar utilities package, so I can immediately use that without defining it separately in this file. Okay, so all right, so let me just check what phi is. So there it is, a very generic function phi. Now what I will do is, I'll just take a look at the form of this sigma rr as it depends on this phi. This sigma underscore rr is a function definition already defined in this polar utilities package. I'm just calling it here. I'm calling it here and making it operate on this generic function phi I have just defined. So you see, this is the form. Okay, so let me utilize this form, this 1 by r del phi del r plus 1 by r square del square phi del theta square. Let me utilize this thing here. Okay, 1 by r del phi del r plus 1 by r square del square phi del theta square. Now this thing, this sigma rr, it has to be, as we have just found out, it has to be of this particular form, which means that this 1 by r gets cancelled. We are left with this. Now see, this is a very, very interesting situation. What do we have here? So this is del phi del r, okay, and there is a 1 by r del square phi del theta square. Fine. Now what could be the possible form of this phi such that when we differentiate this phi with respect to r, that r dependence in it goes away? This is the question we want to answer, because you see on the right hand side we have a function which is purely dependent on theta. That can only happen when this term, like del phi del r, from that the r dependence completely goes away after this differentiation with respect to r. Here also you note that if we have such a phi, okay, so we need to have such a phi that from this partial derivative with respect to theta, automatically what should happen is that whatever r dependence comes out, that has to be negated by this 1 by r. So the consideration of both these facts, or the clues associated with both these terms, it tells us that there is only one possibility here. So you think about it a little bit. There is only one possibility here, and that possibility is that phi must be of the form r into some function of theta. So we call that g. So if phi is r times g theta, then what is going to happen is that when you differentiate this phi with respect to r, this r goes away, it remains, this g theta remains, and when you differentiate this phi with respect to theta twice, all right, we have this d square g d theta square, but this r dependence, it comes out and it gets cancelled with this 1 by r. So overall, on the left hand side, we have a pure dependence on theta, which is consistent with the fact that on the right hand side also we have a pure dependence on theta. So this is our second major achievement in our detective work. Okay, so, and this is actually the starting point of the work that we can do in our Jupyter notebook. So we go back to that. We go back to our Jupyter notebook, and instead of this generic, this generally defined phi, we specialize it to the particular form that we really want. Okay, so first of all, of course, we have to define this g. So this is r into g. All right. Now, as we have done so many times earlier, our first job will be to actually satisfy the polar biharmonic equation. Okay, so let's set up an equation, the polar biharmonic equation, like this. So we put a comma, and again, as we have done earlier, on the left hand side of the comma, we will utilize our polar biharmonic definition or function definition, as we have already done that in the polar utilities package. And on the right hand side we have 0. Okay, so this is our biharmonic equation. Let us display this. So you see, it is such a nice thing. If you had actually done this by hand, this 1 by r cube on the left hand side, which is common in all the terms, that you would have simply cut out, and all that would have remained is just this nice ordinary differential equation containing the various derivatives of g theta, and of course this g theta term itself. Okay, so now our immediate job will be to solve for this g theta. Okay, that's exactly what we are going to do. So let's try to solve this thing. So this is a simple differential equation, and we use the dsolve command to solve this. Let's see if this gives us any solution, and see how nicely it is giving us. It is, so you don't even have to worry about manually cutting out this r cube. It has already taken care of it itself. Okay, so if you had proceeded, so maybe what you could have proceeded by hand, maybe what you could have done is to write this this g theta as something like so if I go back here, maybe I go to a new page. So for the g theta differential equation, so this is d4 g theta d theta 4 d4 plus twice d square g d theta square plus g is equal to 0. Okay, so what you could have possibly done is to take something like g is equal to maybe theta to the power m, something like that, or sorry, you could have taken that to be something like e to the power m theta, and if you had substituted it here, then you could have obtained a nice algebraic equation involving m. So this is actually very easy to do. So you'll get a m4 out of this, you'll get a m square out of this, and this is going to be simply 1, and you can obtain the solutions of m easily from there. So you are going to obtain actually 4 different solutions of m, and you can go back and write down the general solution out of that. So that's exactly what has been done for us in SimPy. The solution is given to us. Now what we'll do is we will rewrite this solution in a slightly different fashion. Okay, so what we'll do is, you see there are 4 different constants here, c1, c2, c3 and c4, and all of these terms have been written in terms of this e to the power I theta, e to the power minus I theta, and that's fine. That's exactly the thing that you would obtain by hand. But what I would like to do is to use the expansion of e to the power I theta as cos theta plus I sin theta. Okay, and rewrite the solution for g theta in terms of cos theta and sin theta. So if we do that, okay, so what we'll get is, let me first define 4 new constants a, b, c, d. And let me define a g new in this fashion. So a into cos theta plus b into theta into cos theta plus c into sin theta plus d into theta into sin theta. So that's the solution that I want to that's the solution form that I want to deal with. Okay, and you can actually easily see this if you come back here. So c1 plus c2 theta e to the power minus I theta. So terms like that. So c1 plus c2 theta e to the power minus I theta. So sorry, here. And c3 plus c4 theta e to the power I theta. What you can do is, this one you can expand like cos theta minus I sin theta, cos theta minus I sin theta, and this one you can expand like cos theta plus I sin theta. And if you multiply out the terms, you will end up and algebraically simplify it, you will end up with a form like this. Okay, so now we want to have a new file. Okay, so this is what we want, and let me display this this new solution form that we have obtained after solving the biharmonic equation using the IPython display style. So as we have done so many times earlier, all right, So that's what I want. Now, so please note that there is an r present here. Okay, so now with this solution form for phi, I want to take a look at what are the solution, or what are the forms for the various stress components. So let me see that quickly. And again, I use my IPython display style. I quickly copy paste this to reduce the typing. Let me finish that up quickly. That is sigma r theta. Alright, so you see the sigma theta theta is identically 0, the sigma r theta is also equal to 0, but the sigma rr is something. Okay, and we have to do a little bit of detective work associated with this also. Okay, so let's get back to our writing app and write this form. Okay, minus 2b sine theta by r plus 2d cos theta by r. Very nice. Let me write this down. So sigma rr is equal to, let me just take a look, minus 2b sine theta by r minus 2b sine theta by r plus twice d cos theta by r. Right. And let me quickly take a look back at what I had done in the previous page. So see, at the very beginning of our discussions, we had been saying that no matter what we end up with, the situation must be perfectly symmetric about this x-axis. That was our first clue. Okay, we have not yet utilized that thing. Now, when we are saying that whatever we are getting as our answer, as our stress distribution, that must be symmetric about this x-axis, it basically means that this particular form, this very starting form that we had arrived at as a result of our first major achievement of our detective work, so here the theta dependence captured through this, or represented through this h theta, it must be such that it must be symmetric about this theta equal to 0. Okay, so you note that theta equal to 0, it coincides with this x-axis. So what we basically want to say is that h theta must be symmetric about theta equal to 0. Fine. Now so see, r does not contribute to the symmetry or asymmetry of it. Okay, the only symmetry question arises with this h theta dependence. So what we are saying is that sigma rr should be such that the theta dependence should be symmetric about theta equal to 0. And now in the next page, we have just seen from Jupyter Notebook that we are arriving at this solution form after the solution of the polar biharmonic equation. Now we set ourselves the question, like what are the symmetricities associated with these individual terms. So first we check for this cos theta term. Now cos theta is very much symmetric about theta equal to 0. So this is absolutely fine. Okay, with our fundamental requirement that the sigma rr should be such that it must be symmetric about theta equal to 0. So cos theta being symmetric about theta equal to 0 satisfies that clue. But what about this sine theta? Okay, so sine theta is not symmetric about theta equal to 0, and you can quickly see here. So if you just plot the theta, okay, so we know that our theta plot will be something like this. Okay, where this is 0, this is pi, this is twice pi, and if you continue it like this, it will be going like that. So you see, about the 0, the sine is not symmetric. rather it is antisymmetric. So this is our sine theta plot. Okay, so on this axis is theta. On the other hand, if we consider our cos theta, okay, our cos theta will be something like this. So this is again 0, this is pi, and this is so I have to complete this here. Sorry, I just had a brain freeze. So it's like this. I think I made a mistake. Let me be consistent with this. So at 0, cos theta is 1. At pi by 2, it is 0. At pi it is minus 1. Then it goes up like that. And again at theta equal to twice pi, we have this. So we have this thing. But the important point to note here is that it should be like this on this side also. Okay, so what is basically happening here is that this cos theta is symmetric about the 0 axis. That's the important point here. So this term has to be deleted, this term has to remain, and this term can be deleted. So this term has to be deleted, this term has to be kept, which means that b must be equal to 0. So that is the latest achievement in our series of detective works. So if we go back to our Jupyter notebook, what we can do is, for our sigma RR, we can substitute b as 0, and we have this new form for sigma RR. Now our job is practically complete. All that we have to do is to find out the appropriate value or the appropriate solution for this unknown constant d. And what is the clue that is left in our hand? If we go back to our writing app, you will see that our job is basically done here, because all that you have to do is to satisfy this condition here. Okay, this integration condition we have to satisfy. If we satisfy that, this is one equation standing which has not yet been properly utilized. We have used it to obtain some ideas about the solution forms, but we have not really utilized this equation, and that's exactly what we are going to do. So in previous problems, what we had done in terms of boundary conditions here, so this is like the counterpart of that boundary condition. Note that this is not really a boundary condition, okay, but this is like an indirect form of that boundary condition. But this is definitely an equation, and we have to satisfy this. And please note that it is through this condition that the influence of this external loading is also appearing in our problem solution. So if we go back to our Jupyter notebook, we have to implement this solution through an equation. Okay, so what we do is we write this integration command. Here we have sigma RR. Now this has to be multiplied by R, and it has to be multiplied by cos theta. And note, this integration should be such that theta goes from minus pi by 2 to pi by 2. Okay, so so this thing that we have here, this is the lower limit, and this here is the upper limit. Okay, now this is just the left hand side. Okay, so this is the left hand side. The right hand side, of our equation is just the minus p. But note that we have not yet defined p, so we quickly do that. Right? And we set up our equation very nicely like this, as we have done so many times earlier. Okay, so this is the equation that we need to solve. Let us just display this equation. Okay, before we solve it, let's display this equation. So you see, this is such a simple equation. Pi d is equal to minus p. We could go to an unnecessary step here of writing this like lin solve and doing it, but I mean that would be ridiculous here. Okay, so all that I have to do note here is that d is equal to minus p by pi. So t solution is nothing but minus p by pi. Okay, and all that I have to do for our sigma rr is to for the sigma rr solution is to substitute this d with the d solution and display this thing. Okay, so that's it, done. So that is our sigma rr solution. You see, everything is known here. The p is given to us. Okay, so so depending at what radius from the point of application, okay, so depending on what radius from the point of application of the load you want to find out the stress, you keep on increasing this r. You will be considering correspondingly different arcs, these different semicircular arcs like this, and you'll be obtaining the sigma rr values there. And of course, because of this dependence on theta, you will be having different values along this. But because this is a dependence through cos theta, you will have the nice symmetricity maintained about the x-axis or theta equal to 0 axis. And let us not forget that we have already arrived at these two identities, okay, or these two solutions, that sigma theta is equal to 0 and sigma r theta is equal to 0. So together we have actually arrived at the solution. Okay, so our solution finally is sigma rr is equal to minus 2p cos theta by pi r minus 2p cos theta by pi r. Sigma theta is equal to 0 and sigma r theta is equal to 0. So that is our entire solution. Right, done. Okay, so and as I had mentioned at the very beginning, so this entire problem, okay, so this is a relatively simple problem. If you just revise through it, you'll see that although we had to do a little bit of brain work in terms or detective work in terms of navigating our way through the solution through some special steps, but ultimately it is turning out to be quite straightforward. Okay, there's a lot of cleverness involved in the solution, but the ultimate solution is coming out in a very neat and clean fashion. But this neat and clean solution, it will be the precursor to that entire body of to the entire field of contact mechanics, to geophysical sciences, various problems in geophysical sciences, soil mechanics, as well as various important problems in structural engineering of civil engineering. All right, so with this I'll end this lecture. Thank you very much.